On screen now is some of the equipment that's going to be used for this laboratory exercise. First of all, the hydraulic bench made by Armfield. It's an F1-10 hydraulic bench. This is the device that we're going to be using to send flow through the pipe rack. The way that flow rate is quantified on the hydraulic bench is that there is a tube that indicates the level of water in the wet well in the hydraulic bench, and so the water level will rise in the tube, and the time that it takes to accumulate a certain volume inside of the wet well will be noted, and that is how you quantify the flow rate. The flow rate is controlled from the bench. There's a valve that's pictured there on screen that allows you to increase and decrease the flow rate. That valve will be wide open during this experiment, and instead of adjusting the flow rate with that valve, we'll be adjusting the flow rate with the valve on the pipe rack itself. Okay, the pipe rack, also manufactured by Armfield. It's a C6-10 fluid friction measurement apparatus. This pipe rack has several different diameter tubes, and in this experiment we won't be using the pipes themselves, but we'll be using a number of the fittings. And we'll go through each of those fittings during the experiment itself and showing the data collection. There are three primary pipe pathways that are used in quantifying the flow rate through these different fittings. The third and final primary component in this experiment is the device that we're using to measure the pressure differences between the upstream and downstream tap on the fittings, and this is a Comarch C9555 pressure measurement device, and it's connected to each of the taps with simple plastic tubes that allows a difference in pressure to be measured. A couple of auxiliary items that are shown there. You can see that there is the red bucket. The red bucket is used because it's important to purge air out of the lines that are connecting from the tap to the pressure measurement device. If little air bubbles are in that, then there can be additional fluctuation and introduces an element of error that we want to eliminate. And so when a tap is plugged in, I'll periodically check for air in the lines, and if air is observed, then it'll be purged out of the lines into the bucket. Also, you'll notice that there is a yellow pan, and that's because the pipe rack leaks. You can see duct tape has been used to sort of direct the leaking downward rather than spraying all over the place. Capture the leakage with the pan, and the green towel is to clean up additional drips. From the safety perspective, some of the things we have to keep in mind as we're performing this lab experiment is, first of all, there's electrical energy involved. You can see that it's plugged into a hanging power cord, and so we're going to want to always be cautious to make sure there's no frayed cords or that there's any sort of a shock hazard associated with standing in cooling water and handling the electrical components that we're going to be utilizing. Other safety issues is that the cord is a possible trip hazard. I'll try and tuck that underneath the bench to the extent that it's possible, but still we have to be aware of our surroundings to make sure that there's no trips or slips. Because there will most likely be some additional water spraying out of the bench or dripping from the pipe rack, we have to be vigilant to make sure that none of this slippery concrete gets wet, because that could cause a slip hazard. One other final thing is that this pipe rack is itself a little bit top heavy, and so make sure not to push on it or pull on it. As I'm putting in the pressure measurement tubes, I'll try and support that with my hands. So that concludes the overview of the equipment and a little bit of a safety tour. So what we'll begin now is we'll go through measure the flow rate, and rather you will be observing the conditions that allow you to quantify the flow rate, and then we'll take measurements at each of the fittings that are in this pipe rack. Okay. The bench is turned on, and the flow rating, the flow setting is fairly high. The bench could be turned a little bit higher, but then that just causes a lot of splashing outside of the wet well, and so I turned it down to a high but not extremely messy setting. Contrary to my previous suggestion that we wouldn't be adjusting the flow rate with this valve, looking at the data sheet again, I realized that we're supposed to quantify the gate valve with it fully open. The K values that I have provided for gate valves are a gate valve when it's fully open. And so what I've done is I've opened up the gate valve here in setting 1, flow path A. The gate valve is the one on top there. We're going to be trying to quantify what sort of energy loss there is through a variety of different fittings, including this gate valve, so it's all the way open. Therefore, in order to quantify the flow rate, I did have to use the valve that's internal to the bench. That doesn't change in the calculations that you're going to be doing. I just wanted to mention that for sake of completeness. Now, when I drop the ball inside of the wet well, it's going to allow water to begin accumulating. You'll see it on screen. It's going to first go through these slow flow rate graduations of 0 to 6 liters, but you will note the time that it passes the 0 mark on screen, and then you're going to measure how long it takes to accumulate 25 liters inside of the wet well. So I'll go drop the ball on that now. You should have a stopwatch handy, some sort of a way of measuring the time, hopefully more precise than just looking at the time counter on the screen as you're watching this video. All right, I'm dropping the ball. So the water has begun accumulating in the lower wet well, where the water level rises faster because of the reduced cross-sectional area, but now it's about to cross the 0 mark there. I'll let you indicate the beginning with your own stopwatch. Meanwhile, I'm going to be collecting data during this experiment just for my own purposes. I won't provide that data to you, but I'm curious to know what sort of results I get. Yeah. Hard for me to resist an experiment. All right, so now what you should have done is observed how long it takes to accumulate a certain volume. I'm going to open the plug on the wet well now. We've quantified the flow rate, and since I'm not going to be changing any of the fittings as we take pressure measurements, the flow rate won't change. If I change the position of any kind of a valve, then I'd need to re-quantify flow rate, but that's not going to be happening. Let's just tour briefly through which fittings are going to be having their pressure quantified. First of all, we're going to go through the 45-degree Y. And let me bring that up on screen here, the 45-degree Y. And you can see the tap upstream and the tap downstream. We're going to be going in a straight line. We haven't yet directed flow sideways out of that, so that is the 45-degree Y. Item 6 on your figure, included with the lab handout, is the long radius 90-degree bend. Next, we'll move on to the ball valve. The ball valve is here. The ball valve is currently open. Next will be the 90-degree T. The 90-degree T is shown on screen. With the 90-degree T, we're going to be quantifying the energy loss for flow that's going straight through a 90-degree T. So it won't, will be again being in a straight line. The upper and the lower taps are the ones that are going to be measured here in just a moment. Okay. The next fitting is the, I'm sorry, I've mixed something up. We've missed the 90-degree miter. Okay. The 90-degree miter is here, this very sharp edge transition. So we'll also be quantifying the 90-degree miter, the T, which we already saw, and then the, whoa, I'm gonna get dizzy watching this video. All right, that is the short radius 90-degree bend, and finally, the energy loss through the gate valve, which is that upper valve, and you can see the tap on either side of it. Okay, so we will now begin measuring the flow rates at each of, the pressure drop at each of those fittings. Okay, you can see that I've mopped up some overspray out of the bench, trying to keep things so that it's not too slippery. When the taps are plugged in, you have to listen for a distinctive snap. I'm going to hear that snap, and it will tell me that it's in. I'll take the downstream snap, go ahead and get that plugged in. Hear the snap.
and I see that there are air bubbles in the line, and so I'm going to purge these lines of air. All you have to do is disconnect it from the pressure meter, and water will flow into the bucket. I'm going to raise it up to try and coax those air bubbles out of the tube. I can see there's actually a pretty long stretch of air in there. Really improve our accuracy considerably to make sure that there's nothing but liquid in there. And I can just plug it back in and it's good. Same thing with the downstream tap. I want to make sure that I get all of those air bubbles up. So I'm lifting the tube high, allowing the air bubbles to rise. Okay, they're gradually making their way to the top of the tube. And as soon as I see that air bubble's out, and I'll just plug the plastic tube back into the pressure meter. All right, it is in. Okay, you can see that the pressure gauge is jumping around a little bit. What I need to first do is make sure that pressure gauge is zeroed. So I'm going to close the downstream valve so that there's no flow going through the pipe. I'm going to push the 0 button so that it's been zeroed. Open that valve back up again. Now, since that valve has just been exactly back to the same position as before, we can expect the same flow rate. The negative pressure measurement means that there is a pressure loss through the fitting, which is exactly what we'd expect to see, is less pressure downstream than there was upstream. And so what you should do, what you need to do is take some pressure measurements there. It's jumping around a bit, and the way that we handle that and overcome it is with a temporal average. So you'll see several different values. Enter 5 or 6 or 10 of them into your calculator and then take the average of all of them. I'll do the same. I'll write down some values on my page, and later on I'll take an average so that I know the average drop in pressure through this fitting. We're working with the 90-degree Y, so writing down data. When the pressure is small like this, it's particularly sensitive to these rapid variations, so hopefully we'll get better data with some of the other fittings where there's more energy loss. All right, hopefully that's been enough for you to gather some data. Of course, you can replay this segment of the video again if you want to get different data or more data. So that's our 45-degree Y. Next we're going to move to the long radius 90-degree bend. Rather than unplugging the tap that I've already got in at the lower position, I'm just going to unplug the upper one that's here and move it to this location. Now, swapping what's the upstream and the downstream is going to mean that I'm going to have positive pressures now instead of negative, but that's okay. We still know it's a pressure drop. Let me go ahead and do that. All right. I'll inspect to see if there's any air in the lines, and it seems like I didn't get any air in the lines, so I'm in good shape there. Let's again get some pressure measurements. I'm going to mop up a little bit more of this overspray, particularly off the instrument, the pressure instrument. All right, let's take a look at some of the data that we're getting through this device. Seems like we're losing a little bit more pressure through here than we did through the other one. I'm going to double check the 0. So closing the valve should, once it stabilizes, take it down to 0. It is. That's good. Open the valve back up. And let's take 5 measurements so that we can get an idea of the average pressure loss through the long radius 90-degree bend. Okay. Now all of this is still at the same flow rate that we quantified before. Okay, next moving on to the ball valve. The ball valve is here. I'm going to have to move both of the pressure taps. Okay. I've got those taps in and I am seeing a pressure differential. We'll make sure that it is still zeroed. Let me move that tube out of the way. And we can see that the pressure is jumping around. I'll close the valve, make sure it's zeroed. Hello. I guess that means 0. All right, so we'll gather some measurements here that we can use as our average differential through the ball valve. Turn the meter back on. Okay. All right, so I've gathered 6 measurements there. You could potentially get even more. Next, on to the 90-degree miter. So the 90-degree miter is this one. Again, I'll just switch one of them since I'm already plugged into the upstream tap. I'll move that one there. We are plugged in. We'll find the pressure differential. Wait for it. There we go. All right. Let me prop that up so that it's easier to see. I think that it's at a bit of an angle there. Is that a little easier to read? All right. Gather some data. This is the 90-degree miter, fitting 14. All right. "90-degree T is next. 90-degree T, we're already plugged into one of them. Let me go plug in the other. All right. I'm going to visually inspect the line to see if there's any significant air bubbles that need to be purged. Again, it looks like oh, I do see one. Actually, I see 2, so I'm going to go ahead and purge those. Good data is the essence of experimentation. All right. Purged. I have to flick it to get these ones to move. There they go. Come on. These ones are stubborn. I'm not getting much flow through this fitting. Try plugging into a different tap. I don't understand why I'm not getting more flow than I am. Well, now it's going. It might be that this tap is got mineral deposits or something behind it, because when I plugged in, I wasn't getting any flow from it. So we may not be able to quantify the flow rate through this bend. Let's just see if there's any data. When I turn off, any difference in the data when I turn off the flow versus when it's running. Okay, so I'm turning on the pressure meter. Let me tip it up again. Okay, we are getting some pressure measurements. Let me close the valve so that there's no flow, and that should go back down to 0. Okay, so closing the valve. Not quite 0, let me 0 it. Okay, it's maintaining 0. I open the valve again to its original state. Let's go ahead and gather the data, but then put maybe an asterisk next to the 90-degree T that I wasn't able to get flow through that upper tap. And we are measuring a pressure differential, but it might be that whatever hole there is between the tube and the pipe is very small, and so it was a low flow rate, but I can still measure a pressure differential. Anyways, let's get some of this data. Okay. Next, the short radius 90-degree bend. All right, I will plug in the taps to it. Now each of these fittings that we're doing thus far are going to be energy losses, and so really its pressure is decreasing. I haven't been real meticulous in noting which tap is the upstream tap and which is the downstream tap, simply because I know that all of these are going to induce an energy loss. And again, I've got a air bubble that I need to get rid of. So what I'm saying to you is that the sign of all of these, it's going to be a pressure loss, and so it's a head loss that's occurring. In each case, whether the sign on screen has been negative or positive. I think I'm clear of significant air bubbles. So very low energy loss on this one. Let me turn off the flow so that we demonstrate that the instrument is still zeroed. So flow rate off. Ironically, it's not well zeroed. Okay, it's 0. Turn it on. Okay, we are seeing some pressure difference through here. This is the short radius 90-degree bend. And finally, we're moving on to the gate valve. Gate valve, there we go. Okay. Plugged in the gate valve, checking for air bubbles. Line seems clear of air. See how much pressure difference we're seeing. Again, I will cancel the flow to see if the instrument is still zeroed. That's difficult to read. Let me see if I can get a little bit better angle on it. Okay. Closing the valve. We zero the device. Device is malfunctioning. Let me turn it off, turn it on, zero the device. Okay. I'm gonna have to pause the video and see if I can troubleshoot the pressure measuring device here. All right, there was some crud, I think that's the technical term for it, behind these taps screw in. It's just like a threaded plastic, like a vinyl or something that screws in to these holes in the pipe, these mounts. And so I cleaned it out, and we'll plug in the tap and see if it works again. It's safe for sore eyes. Previously no water was coming out, so now that we're getting water out, we should be able to get a pressure measurement at the gate valve. Previously the instrument wouldn't zero, and that's because one of the sides of the device wasn't measuring pressure at all. So if I close the valve and the flow stops, it is now holding a zero or pretty close to it. And I open back up and we're measuring a pressure difference. Now I did turn off the bench for just a moment, but I didn't change any of the valve settings. I left the bench flow setting the same. All the valves are as previously, and so we will assume that the flow rate is the same as was quantified previously. So now this is the final fitting on pipe path A gate valve, item number 21. So measure the flow difference, the pressure difference there. Okay. The first of the fittings that we're going to characterize pressure loss through here on pipe path B is the 45-degree elbow. I'll connect the taps. Now, I'm going to have to quantify the flow rate again because I've got a different path, a different flow path. I previously have been using that valve on the lower pipe. Now I'm going to open up the valve above it. This is open. And now that I've got water flowing through a different pipe, our flow rate's going to have to be quantified again. Another change I'm going to make is that water has previously been going through the upper gate valve, and now I want it to go through the lower globe valve. And so I'm going to open up the globe valve all the way. The globe valve is open, and I'm going to close the gate valve. All right, so you can just sort of audibly hear that the flow rate has changed slightly. And let's go ahead and quantify that flow rate. This is the flow rate we're going to use for flow path B. I'll drop the ball. Have your stopwatches at the ready. And I'm just clearing my stopwatch so I can follow along at home. Okay, you need to indicate a certain volume collected in a certain amount of time. So it doesn't matter if it's from 0 to 25 or from 1 to 23, whatever you know that volume increment is, and the corresponding time it took for that volume to accumulate in the wet well of the bench. I can see some of you really concerned with accuracy, doing a frame-by-frame analysis, trying to figure out when it crossed a certain threshold. All right, I'm going to open back up that plug in there and note the time that it took and the volume of accumulation in my own notes. And we will move back over to the 45-degree elbow. Okay, so again, we're going to be characterizing the pressure drop through the 45-degree elbow. We'll move over here to the instrument. Pop it on, zero it, and begin taking some data. Instrument on. Kill the flow rate momentarily. Zero the device. It's holding at zero, more or less. All right. And we can write down several values with which to calculate our average pressure drop through the 45-degree elbow. Next, we'll be doing fitting number 22, which is the 90-degree elbow. Here's our 90-degree elbow. We can plug into it. All right, I'm plugged in. And I will zero the instrument, and then we'll measure the pressure drop through there. Looks like this is going to be a big one. Okay, kill the flow, make sure the instrument is reading zero. All right, it is not, which may mean that once again we've got a plugged valve. So let me pause the recording and troubleshoot. Okay, only one of the tubes is leaking water. They both should be when they're taken off of the pressure measuring device. So it looks like the one that isn't discharging water is the taps are clear and open for business. I can get a pressure measurement through that 90-degree fitting now. So let's plug it back into the pressure measurement meter. All right. Turn it on, and let's see if we can get a zero. Lots of water on the floor. I'm going to take a moment to consider my safety and the safety of others, mop up this wet concrete so that there's no slips, trips, drips. On here called filter button. I wonder if that would make it jump around a little bit less. It's maybe like smoothing on the fly. It casts out the, maybe it's an average on its own. Under that assumption, I'm going to leave the filter button on for the rest of the experiments, and that should make it easier for us to gather some data. And in fact, if you want to overwrite the data that you've just collected for the 90-degree elbow, now you've got some values there with which to work. Always learning something new in the lab. Okay, and finally the globe valve. We are connected to one of the taps on the globe valve. Let me plug into the other. And we'll double check to see if we have a good zero. before recording the data. Flow off, 0, no 0. Need to clean one of those taps. Turning off the bench. I'll be coming back to the same setting. Unplug this. Of course, thermometers are meant to poke into pipes. I can see a fair amount of mineral accumulation and crud back there, so I'm just jamming it around. I'll turn the bench back on and hopefully it'll blow some of that out. I can hear already it sprays, that's good. Plug it back in. It'll be interesting to see which of these different gate types loses less energy. Won't it? All right, that's repaired. I'll plug in and turn on the bench and see if we can zero it out. I'm going to purge air. Since I was disconnected for an extended period of time, I do see some air bubbles. Okay, getting flow through both of the tubes, which is a good sign. I see the air bubbles exiting. Plug back in. All right. Trying 0. I need a camera crew. Okay. Killing the flow. We'll zero the instrument. I think when it's on this filter mode, it may take a couple of zeros. Now it's really zeroed. So we are losing pressure through there. And we can quantify how much. This is the globe valve fitting 20. And it's jumping around even with the filter setting activated, so one can only imagine what it would look like without it. In fact, let's take a look. It's jumping around. Filter smooths that out a little bit. We've got data now. Finally, sudden contraction and sudden enlargement. These are along the pipes. Here's our sudden contraction. Here is our sudden enlargement. Okay. So let me plug into the sudden contraction. Again, we're going to have to quantify the flow rate. I'm going to be changing which valve is utilized. I want to send flow through the pipe where the sudden contraction and enlargement are at. So since I'm sending water through such a smaller pipe, the flow rate is much lower than has been. So quantify the flow rate. And can you hear me? I sure hope that you haven't been losing audio periodically. That would be very bad. Get zoomed in so you can see well. Okay, I'll drop the ball.
Since the flow rate is lower here, it's going to take longer to accumulate, so you may want to use a reduced volume for calculating so it doesn't take so long. Note when it crosses 0 or some other point of reference. I need to reset. I'll be starting my measurements at 5. Just based on human reflex, you should typically use times of 20 seconds or more. As long as you do that, then stopping it early, starting it early won't be too significant compared to the overall elapsed duration. It'll be a small fraction of it. So I'm going to do mine from 5 to 20, which means I had 15 liters. Okay. I'll leave it to going up to 25 for those of you who are all the way accuracy. I'm opening up the wet well, setting up to measure the pressure differential through the sudden contraction. Plug into the sudden contraction. And hopefully you don't have to replace any more of these valves, but I'm getting pretty good at it. Inspecting for air bubbles, don't see any big long patches of that. Pop down to the instrument. Zero it out, make sure that it's adequately zeroed. Closing the valve just temporarily 0. It's holding it 0 pretty well. Put it in filter mode, 0. Alright. Now I'm opening up. Now this is one of the cases where it's important for us to note which is the upstream tap and which is the downstream tap. So let me untangle this. And we'll just take a look. Okay, so I've got the taps switched right now. I'm going to swap them so that this is the one that's indicated plus on the meter, and this, the downstream one, is indicated as minus on the meter. So essentially what it's saying, what we're measuring, follow the tubes to where they're plugged in. You can see there's a plus and a minus. The plus is going to the upstream tap, the minus to the downstream tap. When we do that and there's a pressure drop, then it will indicate negative on the instrument. But what it's indicating right now is a pressure increase. There's a pressure difference, but there's a pressure increase. So think about that in the context of Bernoulli's equation. So this is our sudden contraction. Measure some of the values there briefly. Okay, got values. Get set up to plug into the sudden contraction. There it is.
I've zeroed the instrument, so this is the data that we can take. This is our data to record. Let me tip it up a bit so it's easier for you to see. All right, so that concludes what we're going to be doing for the high flow rate measurements. And when we pick up, we're going to do the low flow rate measurements. Okay, so now we're going to quantify the flow rate for the second round here for the for the low flow rate. So you'll need to get your stopwatch at the ready for when it crosses the 0 mark. Zoom in just a bit to make the view a little bit better. Okay. And since the flow rate is lower, obviously it's going to take more time to accumulate the same volume of water, so maybe I won't wait for it to go all the way up to 25. We can get a nice accurate flow measurement for less flow. I've taken my data. Of course, you can continue for more accuracy, go with longer times and more volume. Okay. All right. So the flow rate has been quantified. I will pull the plug from the drain outlet, and we are going to start over at the top. Well, starting at the beginning, this is fitting number 4, the 45 degree. I've already plugged in the pressure measurement taps, and we will get a view of the gauge. And I'll make sure that the 0 is set. Okay. I've once again opened the bottom pipe so that we're getting flow through this bottom pipe, and later on I'll let you know what the diameters of pipes are so that you can calculate the velocity that goes along with each of these different pipes that we're using. So I close it briefly, make sure that it is zeroed. I'm going to set it into filter mode to smooth it out a little bit. Okay, it's relatively zeroed. Turn the flow back on, and we can get the data here. All right. We've gathered the data just now for the 45 degree bend. We'll move on to the long radius 90 degree bend. We're already connected to one of the taps, so I just need to move the other. Okay, that's set. We'll make sure that we're zeroed. Setting it to 0. Zero the device. Because of the smoothing, it takes a minute for it to get actually a 0. It's remembering some of the measurements that it's seen. We'll wait for that to stabilize just a moment. Long radius 90 degree bend. Okay.
Next, we will be calculating or finding the pressure loss for the ball valve. The ball valve, this is fitting number 12 on our list. Okay, I'm inspecting for air bubbles and don't see any. Let me bring that pressure meter a little bit closer so it's easier to read. We need to be looking straight down to be able to get a good view of it. Okay, I'm going to double check as usual the zeroing to make sure that it's zeroed appropriately. Okay, so when I cut the flow, it's zeroed. Open the flow, give the filtering a moment to stabilize, and we can begin writing down data. All right. So again, this is the ball valve fitting number 12. Okay. This filtering makes it nice, right? Fitting 14, the 90-degree miter. Move camera. Okay, already plugged into one of those taps. I'll snap into the other. All right, I've noticed that there's an air bubble in one of the lines, and so I'm going to purge it. I'm getting good flow, which is to be expected since we have already been through the taps the first time. Cleared out a couple that had the accumulation of minerals and probably bacterial slime. Okay, we're connected in. Get this a little bit closer. Okay, I need to turn the instrument on and we will get the data. Killing the valve, seeing if it's zeroed, re-zero device, open it, let the data stabilize, and this is going to be the 90-degree miter, fitting number 14 on the list. Okay. So I'm beginning to gather my data. I'll filter. That settles things right down, doesn't it? Very good. Next we have the 90-degree T. This is fitting number 13. Okay, I've noticed an air bubble in one of the taps, and so I'm going to purge that. Bubble's making its way out of the tube, and there it goes. Okay. And zero the instrument as we do. Closing the valve, killing the flow, seeing if the data will set to zero and stay there. Some indications that this tap may be plugged. This is the one that I think we may have had trouble the first time around. So let's clear this valve. I'll pause the recording.
Okay, sure enough, there's no flow coming out of this top tap, and so that means we're going to have to probably throw out the data from the high flow rate run that we did on this fitting. It was the 90-degree T. So since it wasn't fixed the first time around, we'll throw that data out. Let me just clear this. Okay, the fitting is cleared. We'll have a look at whether the device can be zeroed now. All right, turn on filtering, close it. It will zero. Open it. Very small loss through this fitting. And I suppose that tells us particularly that in the previous time we had bad data, the pressure difference from the previous run that I was writing down was in the order of 24, 25 kPa. Now that we've confirmed that it's cleared and have the filtering turn on, for the low flow rate, the 90-degree T is getting values in the 0.58, 0.51 range. All right. Our next will be the gate valve, the short radius 90-degree bend. Plug in. Zero the instrument. Okay, it's zeroed. The flow is back on again. Now these pressure differentials are going to be lower. Since we've got a reduced flow rate, we should expect there to be less energy loss. But in theory, the K values need to be independent of velocity. They are in fact supposed to be constants, and so we'll put that to the test and see whether it's actually the case. Next is the gate valve. I'm checking for bubbles. Don't see any. And we will check for zero. Okay, the instrument is zeroed. Now we're measuring the pressure drop through fitting 21 gate valve. Okay. Since the values have settled down using filtering, I'm actually now recording only 4 values, whereas previously I was recording 6. And I don't know if your method has changed, but this is something that maybe you can address in the body text of the report. Be the flow rate quantification for the low flow rate flow profile B. In that one, I used 10 liters. You could have used 15 if you had your stopwatch handy at the very beginning. I recorded how long it took. All right. Now that I've got the flow rate quantified, I can do the 45-degree elbow. I'll zero the instrument. By closing the valve, checking that it's at 0, it is. Opening the valve, I'll turn on filtering to make sure that the data is even a little bit more stable than otherwise. In filtering, it's just doing that on the fly averaging on your behalf for you. It's awfully nice. Okay, that's the 45-degree elbow. Moving on now to the 90-degree elbow. Tapped in. Check to make sure that it's zeroed. Closing the valve. Gets down to 0, that's good. Open the valve. And we'll now take the data. This for the pressure loss across the 90-degree elbow. Globe valve is next. Already connected to one of the taps on the globe valve. I'll now connect to the other. Check for 0. Zero looks good. Open the valve. And we can begin gathering the data. Oh, shoot. Turned itself off. Just to make sure that the 0 is still good, I'll kill that again. Yeah, it goes down to 0. I'll turn on filtering. The valve again. All right. We're now recording data for the globe valve. Comparing that to the pressure differential in the high flow rate, it's lower than it was, which is good. That's what we'd expect, that the lower flow rates are going to have lower pressure losses because the velocity is decreased. Next, we need to quantify the flow rate for the final flow path, flow path C. In flow path C, what I'm going to be doing is opening up the flow to go through this pipe, which is where the sudden contraction and sudden expansion are at. So I've got flow going through the sudden contraction pipe. We'll now quantify the flow rate for that. You, of course, can continue your measurement even longer than I have, up to 15, let's say. All right. Now we're going to measure the pressure difference through the sudden contraction. Turn the instrument on. I'm going to check the zero, closing the valve. If we do go down to zero, I'll just turn on filtering, re-zero it for maximum precision, open the valve, and now we're gathering data for the sudden contraction. I'll now plug into the expansion. Check zero. We can probably do better than that. It's perfectly zeroed now. Okay. We're gathering data for our final measurement. This is the sudden expansion. Okay. Okay, this shows the pipe diameters, and included in the lab handout is the diameter of pipe through which each fitting is associated. And so you're going to have to know the velocity as the water travels through the fitting in order to relate the pressure drop to the K value. And so here's the key to the different pipe diameters and where they're located. That bottom pipe is a 15 millimeter inner diameter artificially roughened pipe, but that is really just some sand that's glued onto a 17 millimeter inner diameter stainless steel pipe. And so the majority of these fittings are on that 17 millimeter pipe. The sudden expansion and contraction, that line is on the second one down, which is the 8 millimeter diameter. You can see that it's a transition from a 17 to an 8 millimeter at the sudden contraction, and the sudden enlargement is transitioning from 8 millimeter to 17 millimeter. That's the conclusion of this lab experiment. Just to recap what we've done, by measuring the pressure difference through a fitting, we're able to use the local loss equation, which says the head loss is a function of K times the velocity head. Since we'll know the velocity, and we've just measured a pressure difference, which can be used to calculate the head loss, then the unknown in that expression will be the K value. So in this way, we can characterize an experimental K value for each of the fittings that have been tested, both at a high flow rate and a low flow rate, and then compare that experimentally determined K value to a K value in the published references that are already known. If any of the data doesn't make sense to you, or if you weren't able to capture the data from the video that you watched, this equipment will be available in the lab, and it's out in case you'd like to repeat any of the experiments and gather your own data independently.